guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to a little continue our discussion about manifold learning methods and review some of the methods that we learned, and also we will learn how to use them with scikit-learn, and then we will take a quick look at tSNE. After that, we will learn about binary classification metrics or classification metrics. That is very important if you want to compete in the competitions or do a real world application. Okay, so first we want to talk about tSNE, or t-distributed stochastic neighbor embedding. So we don't want to actually go through the mathematical detail of this method. You could read the paper of this method if you want to dive into the whole details, but just we want to mention the overall view of this method. Okay, so what is tSNE? It is a nonlinear technique, so it is nonlinear. If you remember, in the last session, we talked about local linear embedding and MDS. The MDS was linear, but we could actually use a mapping to make it nonlinear, and also we had LLE, which is nonlinear. Okay, so the tSNE also is nonlinear technique for dimensionality reduction that is particularly well suited for the visualization of high dimensional data sets. So it is extensively applied in image processing, NLP tasks, or speech processing. So if you take a look at many papers in image processing or in deep learning area, you will see that in lots of papers researchers use tSNE to visualize the high dimensional data like images in 2D. Let's see, maybe it is good to see. You probably have seen some images that are represented in 2D, like this one. Okay, so or this one. For visualizing these images, in fact, researchers use tSNE to reduce the dimension of images. So if we have images, let's say 28 by 28, we want to reduce the dimension of them to visualize them to 2D space. Then we actually represent all of them in 2D space, and actually we could, instead of this point, we could use the mini picture of this image in here to have a better look of this image. And as you could see in here, we have some kind of relation for the close points. For example, as you could see here, this is a car. I don't know whether you could see that or not. It is really small, but this is a car or a vehicle, and also this is a vehicle, and they are close together in this two-dimensional space. So this means that the tSNE actually is a really powerful method that are able to gather all the related things together. So it is really extensively used in image processing, NLP, and speech processing. Okay, so the brief overview of working tSNE is as follows actually. So the algorithms starts by calculating the probability of similarity of points in high dimensional space and calculating the probability of similarity of points in the corresponding low dimensional space. So note that in MDS we calculated the distances between the points in the high dimensional space and in the low dimensional space, and we wanted to make them as close as possible together to build the low dimensional space. But in here we calculate the similarity of the points in the high dimensional space, or the probability distribution in the high dimensional space and in the low dimensional space, and we want to close them as much as possible. Okay, so the similarity of points is calculated as a conditional probability that the point A would choose point B as its neighbor if neighbors were picked in proportion to their probability density under a Gaussian distribution at A. Okay, so it tries then to minimize the difference between these conditional probabilities in higher dimensional and lower dimensional space for a perfect representation of data points in lower dimensional space. So how should we actually minimize these two, the difference between these two probability distributions? We use KL divergence, as I think we have learned about KL divergence in previous sessions. So to measure the minimization of the sum of the difference of conditional probability in tSNE, tSNE minimizes the sum of KL divergence of overall data points using a gradient descent method to minimize the difference between the to minimize the KL divergence. So in actually simpler terms, tSNE minimizes the divergence between the two distributions. So first one is a distribution that measures pairwise similarities of the input objects, and a distribution that measures pairwise similarities of the corresponding low dimensional points in the embeddings. Okay, so the general principle of also the tSNE is somehow like MDS, but in MDS we actually wanted to make a low dimensional space that the distances between points are preserved in this transformation, but in here we try to build somehow of similarities between points or probability distribution between points, and then we want to preserve that when we want to transform the data. Okay, so let's see how to use LLE, MDS, or tSNE with SKlearn. Okay, first we want to see the MDS and how to use that. For this we use a data set. So from SKlearn.datasets we import low digits, and to use MDS from SKlearn.manifold we import MDS. Okay, now we load the digits and the dataset. So now if you print the shape of X is something like this. Now if we want to use MDS, first we create an object for MDS. The argument that is important for MDS is number of components that you want to reduce the dimension to how many dimensions that you want in low dimensional space. Let's say we want to have 2 dimensions to be able to visualize the transformed data, and after that we want to have transformed data is equal to embedding dot, we want to first fit and train the MDS and then transform the training data with that. So we use fit and transform. So actually you could done this with 2 different lines, but this is more easy. So you could actually use that fit of X, and after that this actually fits the MDS on the data. Then you could use the transform method to transform the data. Let's say we want to just do this on just 100 data points. Okay, it seems that we should use it in here. Okay, now we have the transformed. Let's print the shape. Now if we if we want to visualize the data, we could use matplotlib as then we want to have the first component as X and the second component as Y, and to have a better look. Okay, so this is actually the result of MDS when we transform the data. Okay, now let's see how to use LLE or local linear embedding to reduce the dimensions of the data. Okay, the usage of local linear embedding is pretty similar to the MDS. So in here, instead of MDS, we could use local linear embedding, and in here we just use local linear embedding. Let's do this again, and now we have really different result from the MDS. So choosing the right method is really important, and also these methods have some parameters that are really important to tune. So if you want to use LLE or MDS, you could fine-tune their parameters or read about their parameters in the SKlearn documentation. Okay, and also for tSNE, we have the usage of tSNE is actually really like these others things, and you could see in here, should convert that to search it in SKlearn, and okay, it is capital. Okay, now we could see the result of tSNE. So the different methods are pretty similar together for usage, but they are really different when you want to get the result. So let's see the comparison between the manifold learning methods. It is really good to see. So as you could see in here, these are the original data points in high dimensional space. In this case, they are in 3-dimensional space, and they are on a 2D manifold. Okay, so as you could see, this is a 2D S-curved manifold that the data are laid on. And if we use manifold learning to somehow unravel these data points, we could see the different methods of using manifold learning to do this. So in here, this is the result of local linear embedding, and this is the result of LTSA, which we didn't talk about it, but actually you could use it. And here is Hessian LLE or local linear embedding. It is one variant of LLE, and actually, as you could see, it is really good. It is like we actually unravel this S-curve very, very carefully and very good. So it is a good way, but as you could see in here, the performance, if you have a large data sets, then probably these methods took a long time to learn the model, and they could cause trouble for you to reduce the dimension of your data, because they are typically computationally expensive. And here we see the ISO map, which we talked about it, and MDS. As you could see in here, MDS maybe is not, it is not bad actually, but it is not as powerful as other methods. And as you could see in here, the performance of it is really worse than in comparison with other methods. And this is tSNE. As you could see here, the visualization in 2D is not bad, but tSNE takes a long time to train and to calculate the reduced data points. So if you have really large data sets, just be careful when you want to use tSNE, because it probably your kernel in Jupyter crashes maybe, because they are somehow computationally expensive, and yeah, just be careful. So if you don't have lots of data, like maybe for 1000 and for this kind of data with 100 dimensions, it is fine to work with tSNE. But otherwise, maybe other methods you should look. For example, PCA maybe. Yeah, PCA is really worse than tSNE and other methods, because it is just a linear transformation, but it is much more fast than these methods. Okay, so now you have some kind of sense about manifold learning. Okay, the last thing which we want to talk about it today is classification metrics, or in particular today we want to talk about binary classification metrics. So in binary classification, first we want to introduce some terms to be able to define some definitions. So we use the term positive and negative to refer to the classification and your classifier prediction, and terms true and false refer to whatever the prediction corresponds to the external judgment. So we could actually formulate the following table for this definition. So if we have actual class in here and we have predicted class in here, now we could have true positive. So the TP means true positives, which means that correct result. We have false positive, which means that unexpected. Don't worry if you are a little confused about this definition. We will go through that in the shorts. So this is false positives, means that unexpected result. Here we have false negative or missing result, and in here we have true negative, which is correct absence of result. And based on this matrix, we could define precision as true positive over true positive plus false positive, and recall as true positive over true positive plus false negative. Okay, probably you are confused a little now about these terms and what is that, but by an example you clearly could grasp the idea behind this definition. Okay, suppose a computer program for recognizing dogs. So let's say you created a classifier to recognize dogs in photos. So your classifier wants to recognize dogs in photos. So your classifier identifies, let's say your classifier identifies 8 dogs in a picture. In that picture, the total number of dogs is 12. So in general, in the picture we have 12 dogs. So we have 12 dogs, and your classifier recognize 8 dogs. Okay, and also we have some dogs, and let's say we have some cats in this picture. Okay, so let's say from these 8 dogs, so your classifier recognize 8 dogs. From these 8 dogs, 5 of them are actually dogs, and so 3 of them are cats, probably because we have some cats in here. So 5 of them are actually dogs. So these are true positives. Okay, and so the rest of them means that 3 of them are cats. So they are false positives because your classifier said that they are dogs, but they are cat in this picture. Okay, so the precision of your classifier is 5/8. So from all of the detected result of your classifier, it detects 5 of them, it recognizes 5 of them true, so it is 5/8. and your classifier recall is 5/12 because you have 12 dogs in this image, so the recall is 5/12. Okay, so I know maybe you are not really comfortable with these definitions, and in fact they are a little maybe confusing at the first sight, but at times goes you're probably used to how to use them. And also to have a better visualization, you could consider this diagram for so let's say here are false negatives, here is true positive, here is false positive, and this is true negative. So the precision is actually just this part, or true positive over all this circle, and the recall is just this part over just this section or relevant section. Okay, so these two metrics are really important, and for your classifier and for the classifiers there are some kind of trade-off between these two metrics, and to actually combine these two metrics we have another metric called F1 score, and it is defined as 1/1 precision plus 1/recall, and it in the best case your classifier has the F1 score 1, because in that case your precision is 1 and your recall is 1, and 1/1 so this is 2, and the maximum will be 1. Okay, the importance of these metrics will be obvious when you have imbalanced data set. So let's say you want to start or compete in a competition that is credit card fraud detection. Okay, so when you want to have credit card fraud detection, probably your data set consists of lots of non-fraud transactions, like for example your data set maybe consists of 10,000 non-fraud transactions and maybe just 100 fraud transactions. So let's say you train your classifier, and as a metric you use the accuracy to see how your classifier works. Let's say your classifier just says that all of the transactions are non-fraud. So without looking on the input data, it says that it is not fraud. In that case, your accuracy will be on your training data set will be over oops. Okay, if you calculate this, as you could see, your accuracy is 99%. Okay, and you probably say, wow, I have a very good classifier that its accuracy is 99%, but in fact your classifier does not know anything about fraud detection, because it says that always a transaction is non-fraud, and in fact this is not a good metric, especially when you have imbalanced data sets. In that case, you should use F1 score, because if your classifier says that all of the things are non-fraud, then one of the precision or recall will ruin, and so F1 score is getting low. So in those cases, you should use F1 score as your metric. And there are, for imbalanced data sets, also there are some other metrics, but one actually measure to find out your classifier performance is using confusion matrix. So in confusion matrix, let's say we have in non-fraud and fraud case, we have non-fraud in here, we have fraud in here, and non-fraud in here, and fraud in here. And we name this a confusion matrix. So in this case, so this could be your classifier prediction, and this is the real label. So let's say from all of the non-frauds, so you have 100 non-fraud, and your classifier detects 80 of them, and for 20 of them it says that they are so let's say this is your classifier prediction. So from all over these 10,000 non-fraud, we detected 9,000 as non-fraud and detected 1,000 as fraud. And for all of the frauds, we detected let's say 80 as fraud, as non-fraud, and 20 as fraud. So you could say that this is not a good classifier. Why? Because when you look at the main diagonal, the main diagonal means that the true things that your classifier predicts. You should have a really good numbers in here. So you could see that in here you have 80. This is actually not good. It means that you have from all the 100 frauds, your classifier predicts 80 of them as non-fraud. Okay, so this is not good. So if you have a good classifier, then you probably have something maybe like this for a good classifier. Maybe this is 20, 100, then this is 200, and maybe this is 10, and this is 90. And in this case, you probably have a good classifier, and you actually could normalize the confusion matrix to get the performance of your classifier. So when you have imbalanced data sets, assure that you put the right metrics for yourself to evaluate your classifier performance, or if you want to use cross-validation, you use F1 score as the metric. And also, for all of these metrics are available in SKlearn. So you could use them, in SKlearn. So as you could see, if one score or all of the other recall score, precision, and lots of other metrics that you could use. I just wanted to introduce to you some of the most important metrics and why is the accuracy is not enough always, and you should use other metrics when you are using classification. Okay, I hope that you enjoyed from this session, and see you in the next session. Bye.